Hey folks, it's Sam Naser here, software engineer at Google. I'm going to be joined by my colleague Craig in a bit, but today we're going to be talking to you a bit about not shipping your org chart in your open source projects and how Istio made an architectural decision early on that was eventually rolled back for the sake of user experience. We're going to start off with Craig talking a little bit about the original architecture of Istio and how over the course of a few years we ended up where we are today. And then it's going to kick back to me, where I'm going to talk a bit about Istio upgrades over time, then talk a little bit about how Google runs Istio at scale. So please take it away, Craig.
Thanks, Sam. Hi, everyone. I'm Craig Box. I work at Google Cloud on the Istio open source project, and I'm currently leading its transfer to the CNCF. When we launched Istio, we described it as software that provides a uniform framework for connecting, securing, managing, and monitoring service-to-service communication. Now, that was over 5 years ago, so many of you will now be familiar with the pattern, and I can now just say it's a service mesh that runs on Kubernetes. As with many pieces of the cloud-native ecosystem, Istio is a reimplementation of ideas from Google production. To understand why Istio was built the way it was, we need to have a look back at what influenced it. In the mid-2010s, we developed a new API serving infrastructure, which was designed to handle Google's growing cloud business. To save us having to maintain a library for each language that a service team might use, we adopted a sidecar proxy model. That proxy would handle things that were applicable across all APIs: authentication, quota, policy enforcement, load shedding, error sanitization, telemetry, and more. We coupled this with control plane services to act as backends for the proxy, acting as a central point where quota and policy would be defined and enforced, and load balancing infrastructure, the global software load balancer, which we described in the SRE book. Many of the same people who built this system went on to design Istio. Istio was released into a world that now contained Kubernetes, with its declarative control plane, its pods with multiple containers, and its ingress architecture. We identified that IBM was doing some similar work in the space with a project called Amalgamate, so we reached out to that team and they decided to move forward together with us. When we needed to find a proxy server to run as the user's sidecar, we found the Envoy proxy, recently open sourced by ride-sharing company Lyft, and worked with that team to extend Envoy, where necessary, to support the Istio use case, becoming one of its first external users. The Istio block diagram was immediately familiar to someone who had used Google's API infrastructure. From a user's perspective, it appeared traffic flowed directly between services as usual, but in the data plane, we would capture the traffic in the Envoy sidecar where we could perform the mesh functionality. There were two reasons we designed it this way. The first we would sometimes generously call our crystal ball. Kubernetes had an initial reputation for being complicated, especially when compared to other systems of the time that were aimed at solo developers. Google had been running declarative distributed systems for many years. We knew that when you crossed a certain line, which we sometimes refer to as day 2, there are many advanced features that you will need. As long as the system could operate sensibly for new users without encumbering them with knowledge of those features, it was best to have support for them built in from the beginning, rather than a user having to undergo a migration later on. The second was somewhat related to the target audience. Users were going to deploy microservices applications on top of Kubernetes, and indeed we put microservices-oriented as one of the 3 central tenets of cloud native when we set up the CNCF. Microservices allowed many benefits, including developing in different languages, allowing independent scaling and upgrades, and stronger security boundaries between components. Istio's control plane was, itself, a modern cloud-native application, with a need for components to communicate securely and to be observable. Therefore, it seemed obvious that Istio's control plane should be a microservices application. So, where was the problem? Istio launched just over 5 years ago, to great fanfare. Its heritage at Google, as well as the production experience of IBM and Lyft, meant that it was immediately useful to people who had problems monitoring, managing, securing, and connecting the microservices in their modern applications, exactly as we had hoped. But over the next 2 years, Istio gained a reputation for being hard to operate, for performing poorly. In talking to users of the product, we learnt that the advantages that would have applied to a set of teams operating Istio at Google production scale were not relevant trade-offs that applied to everyone. In almost all cases, a single administrator, or a small team at most, was responsible for a whole Istio installation. We built the control plane components to be able to be scaled and rolled out independently. Scaling them at all was unnecessary for most teams, and no one would ever deploy the components at different versions. Indeed, we never tested or supported this use case. The complicated dance required to upgrade multiple control plane components meant that users often thought the problem was just too hard. As a new open source project, we wanted to move quickly, and as a security product, we needed to make sure that in the case of CVEs, that our users would actually patch their environments as soon as possible. The perceived complexity of upgrades led to our users running old Istio versions, well outside their support window, and Sam will talk about that problem in a few minutes. Ultimately, we had shipped our org chart. We'd aligned our development teams along the boundaries of the production teams who were running the Google equivalents, and then we'd built and deployed the services along those boundaries. It was clear something should change. Within 1 year of releasing Istio 1.0, the development team was able to regroup and look at places where the project had real or perceived performance issues. 2 major areas were identified that related to the initial architecture. First, the Google model of using an extension point in the control plane required every API call to be externally validated, albeit with around a 95% cache hit rate. This was very convenient for integration, but put us outside the performance envelope that we needed to operate within. By moving policy decision-making directly into the proxy, and then building a WebAssembly runtime into Envoy, we were able to retire our first control plane microservice. In our haste to provide a system that would scale to true day 2 use, we were not able to be competitive for people who were just starting on their microservices journey. We then looked at the other components, and specifically whether it made sense that they remain independent microservices. They were all written in Go, so there was no language advantage. We didn't have a security advantage, as the components were generally all installed into the same Kubernetes namespace and had near equivalent permission to alter the proxy configuration. We didn't have a scaling advantage. The costs were dominated by a single feature, the programming of the Envoy proxies, with all other components having a marginal cost. So, in Istio 1.5, we consolidated the remaining components into a single binary. It's called Istio-D. This would benefit our users by way of easier installation, reduced configuration, simpler maintenance, and now having only one component to scale. It's important to note that all of this functionality still exists inside the Istio-D binary as different APIs, because in some cases you will want to run a service which only performs one of these functions. Thus, the user gets all the benefits of the microservices architecture without the downsides that don't apply to them. Here's what the change looks like. Microservices are a tool in a tool belt, and they work best when they're reflected in your organizational reality. They apply to Google's API infrastructure, but they may not apply to yours. There are many reasons that an organization might release open source software. Sometimes they want contributions from other users to help share a maintenance burden. Sometimes they just want to publish a reference implementation of a cool solution. But if your goal is to have other people run the software you release, you should consider the differences in how you might operate the software internally compared to how other teams might operate. Some specific improvements we've realized. We had to have cluster-wide Kubernetes security configurations to allow our control plane components to talk to each other. These could now be removed. We are able to better support non-Kubernetes use cases, where we want to run the control plane in a VM, or even a model where we might want to run many control planes inside a single cluster. Debugging is now much easier with a single binary, one of the obvious upsides of monoliths. Finally, we are able to look at our problematic upgrade scenario, and for that, I'm going to turn you back over to Sam.
Thanks, Craig. Now I'm going to take it and give you a bit more detail, a bit more information about upgrades in Istio and exactly how that consolidation of components that Craig described has let us make upgrades in Istio much simpler and much safer over the years. So first, for some background, upgrades in Istio have for quite a while been a significant pain point for users. Kind of user survey after user survey, upgrades have come up as one of the more daunting aspects of operating a mesh. And this has led to some undesirable outcomes, like quite a few Istio installations have components that are running with vulnerable versions. And in these cases, it's actually potentially making the mesh less secure than if you didn't have Istio installed at all. So this is obviously not desirable. And a few reasons that Istio is difficult to upgrade and perceived as difficult to upgrade. For one, it's a critical infrastructure component. So if something happens, something goes wrong during an upgrade, you might just lose your entire cluster. Things just might go down wholesale, and you might just go dark. So it's a high stakes operation. On top of that, you have this natural architecture where you have the control plane and data plane, and these things aren't really upgraded atomically. So you're going to have to think about these moving parts, right? With the control plane upgrade and the data plane upgrade being distinct things. And then also kind of tying back into what Craig was discussing, when you have 6 components, and this is kind of talking about the past architecture, but when you have that many components that make up the control plane, it's just naturally very difficult to upgrade and to coordinate an upgrade among them. So to give you an idea of how upgrades used to look in Istio, there used to be a mechanism called the in-place upgrade. And what an in-place upgrade is you install the new version of the control plane directly over the old version. So at the end of this operation, let's say you are upgrading from 112 to 113. At the end of an in-place upgrade, you no longer have a 112 control plane, you have a 113 control plane, and it's pointing, and the older proxies are all using that control plane. And this has some undesirable consequences, and I'm going to go into kind of the new model of upgrade in Istio, a more recent one. This model is called the canary upgrade, or if you prefer, the revision-based upgrade. And this is a familiar term if any of you are familiar with Knative. It's similar to the concept of a Knative revision. And the idea here is that instead of installing a new version of the control plane directly over the old version, we're going to have the new version and the old version running side by side in the user cluster. And this is actually a really powerful thing that unlocks a lot of benefits for us. So the first of which, simpler rollback. Before, if you're upgrading and you upgrade right over the old version, you no longer have it. So if you want to go back to it, you have to actually downgrade the entire control plane. With revision-based upgrades, if you go to the new version, something's not working, you still have the old version hanging around. So you just change a label on a namespace and say, hey, I want this namespace managed by the old revision, roll things back out, and you should be good to go again. Moving workloads onto the new version gradually. This is another huge benefit. Before, you just kind of had to upgrade the control plane and everything upgraded at once. You just kind of had to hope that things didn't go wrong, or else you had to do that really potentially destructive in-place downgrade. Here, you can actually, when you have 2 different versions of the control plane running, you can pick which namespaces go on to the next version when, and gradually move presumably less production critical namespaces over to the new version before you move the whole mesh over. So obviously this is a production best practice, and this is a much safer way to perform an Istio upgrade than before. So safer gateway upgrades. Gateways, for some background, are typically the ingress point of all the traffic in your mesh and potentially the egress point for some traffic. And from the user perspective, if your ingress gateway goes down, your mesh might as well have gone dark. It could mean a total outage. And it's incredibly important to get the gateway upgrade right. And in the past, this gateway upgrade happened just like a in-place upgrade. You had to roll over to the new version of the gateway and cross your fingers, hope that things worked. With canary upgrades and combined with some other new features, we're able to run gateways on different versions side by side and shift traffic between them as needed. So you can slowly make sure that the new version of the gateway is working. Again, this is something, it's funny because it's something you can do with Istio, is shift traffic between services, but it's not something you could do with the actual Istio gateway until this work was done. So definite improvement there. And then easier version skew requirements. I won't spend much time on this, but essentially you don't have to make sure that control planes and data planes are compatible with different versions of each other. You can just be happy that control plane and data plane are going to be pointing to the same version of control plane and data plane. And if you know the data planes are compatible, you're good to go. So then here's another diagram that kind of goes in a bit about revision tags. Revision tags are another abstraction on top of Istio revisions that let you put a stable identifier. Basically, you can think of it as a pointer pointing to a revision on a namespace. And then instead of changing the namespace label, you can leave it the same and change where the tag points. And I won't spend much time on this, but this is also a pretty powerful feature of revisions. Up to this point, we've kind of gone through a journey here where at first, we open sourced Istio to be implemented as a bunch of microservices, right? And then we realized that that doesn't make sense for most users because most users don't actually look like Google. It doesn't make sense to have 6 different components for your control plane when it's actually one team or small groups of people or even one person managing that control plane. So we made the decision to consolidate things back into one Istio D deployment. But now the funny thing is we're Google and we're going to be running Istio D again, and we're going to be managing it. So now we're back to Google running this control plane. And how does it look now with Google managing and running this Istio D component, right? And to illustrate this, I'm going to go into the architecture of the managed control plane offering. This is an Anthos service mesh product. And this is a product that you probably guess from the name of the product, uses the external control plane deployment model of Istio, where instead of running your control plane in the cluster, you actually run the control plane inside of a separate hosted infrastructure. So in our case, we run the managed control plane inside of hosted Google infrastructure. And this goes a long way in hiding the complexity of the control plane from the user. It's not existing there in the cluster. And maybe most importantly, it makes it so that the user doesn't have to worry about upgrades. With managed control plane, upgrades are transparently handled. And there you go. That's another step in making the service mesh disappear. But the way this is implemented is we have one Istio D per user cluster, essentially managing that user cluster. So this is not a multi-tenant architecture. This is a one Istio D per cluster architecture. We don't have one instance of Istio D managing thousands of customer clusters, for example. And that goes a long way, but we still have certain components of the service mesh running in customer clusters, right? It's kind of the nature of control plane. The nature of service mesh is you have the data plane component running next to or near the user applications. So we have products to help with that, like managed data plane, where a controller makes sure that when a control plane upgrade happens, that the data plane is upgraded promptly to the new version. So you don't have those issues with outdated, vulnerable components hanging around. So it's a very powerful thing. To bring you to some takeaways here, the first thing, your target user doesn't always look like you. When Istio was open sourced, we assumed that the customers would want to run Istio in the same way that Google runs the internal equivalents, and that's just blanketly false. In practice, a lot of our users were running Istio with smaller teams. There's no need to have entire teams of people managing each of the separate control plane components. It just doesn't make sense. Microservices are not the right solution in all cases. This is kind of a tired line at this point in this stage of microservices in the industry, but don't adopt microservice architecture for your project unless there's the tangible benefits that go with microservices, like independent administrative domains for your each of the services and being able to roll them out independently and having teams manage them. If you don't have that, maybe it doesn't make sense to do. And then when open sourcing something, think about how it'll be used. So this is kind of a generalization of the lesson, right? If you're just open sourcing something to open source it, you probably don't have to worry about this. But if you're open sourcing something with the intention of getting widespread adoption, then you need to really think if the architecture of the people you want to adopt it looks anything like yours, and if their organizations look anything like yours. And a hint, most organizations can't afford to spend entire teams managing single components of service mesh control planes. So, and then this is kind of a common sense one, but sometimes walking back an architectural choice is the best way forward. So we made a decision early on in the project that was eventually walked back, and it seemed like the natural choice at the time to use microservices to implement something that is made to manage microservices, but that wasn't the case, and it wasn't actually the best choice for the user. So yeah, that concludes the talk, and thank you for your time today.